Okay, section 7.2, properties of parallelograms. Our objectives for this lesson are to use properties to find side lengths and angles of parallelograms. Use parallelograms in the coordinate plane. Okay, so what is a parallelogram? First off, it's in its name, parallelogram. A parallelogram is a quadrilateral. Again, a quadrilateral is a four-sided polygon. Okay, so it's a quadrilateral with both pairs of opposite sides parallel. Okay, I go over how to create a parallelogram in GeoGebra, along with some of its properties in a video. If you haven't watched that one yet, please pause this one and go back and watch that. Okay, so if I wanted to denote, okay, so now that we're talking about our parallelogram, if I wanted to denote to a reader, anyone reading my paper, that this is in fact a parallelogram, I would need to mark parallel. So I would need to mark this side parallel to this side, and then this side parallel to this one. Okay, so if these are vertices A, B, C, and D, I would call this parallelogram A, B, C, D. Okay, and then we often use kind of this parallelogram-ish small symbol like this to mean the word parallelogram. Okay, so when we see that little parallelogram-y type symbol, that means parallelogram A, B, C, D. But again, I could call this parallelogram D, A, B, C, or C, B, A, D. We basically just go around in a circle one way or the other, listing off those vertices. Okay. And like you noticed in the video, there's some interesting properties about parallelograms. Here we'll talk about the first two here with our parallelogram opposite sides theorem, and then our parallelogram opposite angles theorem. So for our parallelogram opposite sides theorem, if a quadrilateral is a parallelogram, so we start off knowing that it is a parallelogram, which means opposite sides are parallel, then its opposite sides are congruent. So if I know it's a parallelogram, so basically it's if quadrilateral QRSP is a parallelogram, if I know it's a parallelogram, then I know that segment QR is congruent to PS. So here QR congruent to PS, put one notch on them. And segment QP is congruent to RS. QP congruent to RS. Okay. All right, so that's using the parallelogram opposite sides theorem. So if I start out by knowing it's a parallelogram, then I know opposite sides congruent. Okay. The parallelogram opposite angles theorem is very similar to opposite sides, except now we're dealing with angles. So here's the opposite sides theorem, here's the opposite angles theorem. Okay. So if a quadrilateral, again, is a parallelogram, then its opposite angles are congruent. So then we'd have opposite angles, like angle P here is congruent to angle R, because it's across from it, and angle Q is across from angle S. So those are congruent as well. So the opposite angles are congruent. So here, P is congruent to R, and angle Q is congruent to S. And if we label here, let's go this side, go to that side. I'm going to highlight on this other one. So pink congruent to pink, orange congruent to orange. All right. So now we're going to briefly discuss the parallelogram opposite sides theorem. Okay, so we're going to look at the proof for. I'm not going to write out the entire proof, more of a plan just so we get the gist. The entire proof is found in your book on page 368. We're just going to talk about how it's proven. Okay, so we're given that PQ quadrilateral PQRS is a parallelogram. we need to prove that the opposite sides are congruent. We need to prove that QR is congruent to SP, QR to SP, and we need to prove then that PQ is congruent to RS. That's what we're trying to prove. So how we go about doing this is actually by using an auxiliary line, an auxiliary diagonal. We start by drawing a diagonal in. We're going to draw this one diagonal in from Q to S. Okay, so that's our first step. So our first step, we're going to draw segment QS. Okay, and the reason we can do that is, well, through any 2 points, there's exactly one line. Through any 2 points, there is one line. Okay, so that's our reason for that one. Again, this isn't a formal proof. This is just going to be our plan. It's our plan for our proof. Okay, but by drawing that in, we end up having these congruent, we have these triangles. Okay, so, and in these triangles, I know that QS is, so if I'm looking at this triangle, I know that QS is congruent to SQ by reflexive. Okay, so we have this side's congruent to itself, and my goal is to prove that these two triangles are the same, and one way of doing them is using alternate interior angles, because I know that QR is parallel to PS. Since QR is parallel to PS, if we were to draw in, I'm just going to extend these two lines out, my highlighter, so we have this line parallel to this one, not congruent, parallel. We have those two lines parallel, which then means that this angle here, the reason we know they're parallel is because the whole parallelogram part, that'd be definition of parallelogram. Okay, so we know those two orange ones are parallel, which then tells me that angle RQS is congruent, RQS, this angle, is congruent to angle PSQ. Okay, and that's alternate interior angles. Okay. Okay, but then we also know these other two lines are parallel. We know these two pink lines are parallel. This one and, oh, I smeared. My highlighters are smeary. Okay, we know those two pink lines are parallel. So we can actually then put that back up here with this step. We know that QP parallel to RS, again by definition of parallelogram. So then not only do we know these two angles are congruent, we also know that this one, using this transversal, this angle's congruent to this one. Again, using alternate interior angles. So then we can say angle PQS, PQS, congruent to RSQ. Again, alternate interior angles. So now what I end up having, if you notice, I have angle side angle. So the two triangles, triangle PQS would be congruent to triangle RSQ by angle side angle. Well, if the two triangles are congruent, then all their pieces are, which means that this side is congruent to this side, so we can finally, there's our final proof, QR congruent to SP and PQ congruent to RS, and the reason for that is by corresponding parts of congruent triangles. 1, 2, 3, and 1, 2, 3. Since we've proven these two triangles are congruent by angle side angle, all their pieces are congruent by corresponding parts of congruent triangles. Okay, there's the proof in a nutshell. That's our basic plan. We'd want to neaten that up. Again, this is our rough draft. Okay, if you want to see the final pretty copy, see page 368 in your book. Okay. Next, example 1. So now we're going to use these theorems. Okay, so here it says find the values of x and y. First, if we notice, we have arrows. These two are parallel. These two parallel, so I know it's a parallelogram. So we start out by knowing we know it's a parallelogram. So since it's a parallelogram, we know opposite sides are congruent. So I know that this side, which is x plus 4, is going to be congruent to this one. I know AB is going to be equal to DC. AB is x plus 4. DC is 12. Subtract the 4 from both sides. X would equal 8. Okay. We also know opposite angles congruent. So here angle Y congruent to that 65. So that means Y equals 65. All using those theorems. Okay. So we have 2 parallelogram theorems so far. We're going to learn 2 new ones. The parallelogram consecutive angles theorem. Against consecutive is in a row, one after the other. That's what consecutive means, one after the other. Okay. So if a quadrilateral is a parallelogram, so again we start by knowing we have a parallelogram, then its consecutive angles are supplementary. Again, supplementary add up to 180. Okay, so consecutive angles, meaning one right after the other. Like here, angle P and angle S. If I take the measure of angle P and add it to the measure of angle S, we will get 180. If I take the measure of angle Q and add it to the measure of angle P, Q then P, we will get 180. Any 2 angles in a row. If I add, oh, this is an R. If I add angle R to angle Q, we'll get 180. R to S will get 180. Q to P will get 180. Any of those 2 angles in a row will get 180. Okay. And then I believe our last theorem, is if a quadrilateral is a parallelogram, so we know it's a parallelogram again, then its diagonals, if I draw in its diagonals, they bisect each other. So this diagonal from QS is going to bisect this diagonal from RP. What that means is that this point here in the middle, let's call it M, is the midpoint of both of those sections. So Q to M is congruent to M to S. P to M here is congruent to M to R. Okay, so that tells me that M is the midpoint of both diagonals. Be very, very cautious here. The diagonals are not congruent. You can tell this diagonal is much shorter than this one. But what the diagonals do is they divide each of themselves up into 2 equal pieces. Okay. The proof of this is in your book on page 370. Okay. The proof, the parallelogram diagonals theorem. Okay. It starts out with doing those diagonals, drawing those diagonals in, and in the process, we end up using angle side angle again to prove congruence. Okay, to prove that this diagonal does bisect this diagonal, and then this diagonal bisects this one. Okay, so we're not going to look at the formal proof on that, but it is found in your book on page 370. Okay, I don't feel it warrants video time for that. Okay. But this proof does. Okay. Here we want to write a 2-column proof. Given we know A, B, C, D, and D, G, E, F are parallelograms. So we know these 2 things are parallelograms. We want to prove that angle B is congruent to angle F. So I'm going to come in, let's highlight angle B. We want to prove this angle is congruent to this one. Okay. Given that they're parallelograms. Okay, so let's go ahead, let's come up with our statements and our reasons. Let's put together a bit of a sketch of a plan. I'm going to grab a Post-it, so you can go ahead and pause. Grab a Post-it for a plan for this. Okay, so first of all, we know they're parallelograms, and we're trying to do something about the angles. So we know opposite angles in a parallelogram are congruent. So I know angle B is congruent to angle D. This would be the parallelogram opposite angles theorem, right? Opposite angles. Okay, but then we also know angle F is congruent to angle D. Oh, we better be careful which angle D. So let's not just use angle D. Angle B is congruent to angle CDA. Angle F is congruent to angle EDG. okay, using, again, parallelogram opposite angles. But if we notice these two angles in here, this angle and this angle are vertical angles. Angle CDA is congruent to angle EDG because of vertical angles, Well, then I can put these two together. How would we put them together? Maybe transitive property? EDG, yeah, because they're both congruent. This one and this one are both congruent to the same thing. They're both congruent to CDA. So since they're both congruent to CDA, I can say that, put these two together and I can do angle B then is congruent to angle EDG using transitive. And then I can use transitive one more time because here F is congruent to EDG, B is congruent to EDG, so I can say angle B is congruent to angle F using transitive again. So there's our general proof. Now let's write it a little nicer. Okay, so statement again, we'll start with our given. A, B, C, D, and G, D, E, F are parallelograms. It's an F. Parallelograms. One that's given. Okay, so then number 2, so then we know from our plan here that angle B is congruent to angle CDA, B, congruent to angle CDA, and since it has the same reason, let's do it in one step. Angle F is congruent to angle EDG. By my reason there is the parallelogram opposite angles theorem. Opposite angles theorem. And then next we used vertical angles. Angle CDA is congruent to angle EDG by, that's the vertical angles congruence theorem. Or we can just say vertical angles are congruent. Okay. And then my last step, these were both transitive properties, so I'm going to put them together. Angle B congruent to angle EDG. Angle EDG, and then angle B congruent to angle F because of the transitive property of congruence. Transitive property of congruence. Okay. All right, we have 2 more examples left, and that's applying parallel lines into coordinate planes. Parallelograms, into coordinates. Okay, so it says find the coordinates of the intersection of the diagonals of L, M, N, O with these vertices. L is 1, 4. Okay, M is 7, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. Okay, N is 6, 1, 2, 3, 4, 5, 6, 0. And O is 0, 0. Okay, so there's my parallelogram. So here is L at 1, 4. Here is M at 7, 4. Here's O at 0, 0. And here's N at 6, 0. Okay, so here's our parallelogram. It wants us to find the coordinates of the intersection of the diagonals. So I could draw the diagonals in and pray I get lucky and it lands on right where it should. Okay, but I'm just going to draw one diagonal in. Let's draw this diagonal in right here. I know that since it's a parallelogram, the diagonals bisect each other. Since they bisect each other, they're going to intersect at their midpoints. So for me to find where that intersection is, I'm just going to find the midpoint of the diagonal that goes from L to N. Find the midpoint of L to N. So midpoint, add the x's, divide by 2, add the y's, divide by 2. So 1 plus 6, divide by 2 when I add this x and that x. Add the y's, 4 plus 0. Divide by 2, so this would be 7 over 2. 4 over 2 is 2. So there is the coordinates of my midpoint. Or you could write it as 3.5, comma 2. Okay. Right, and if I was to draw in the other diagonal, we can verify and make sure it makes sense. There's the other diagonal. Is it over 3.5? 1, 2, 3.5, up 2. Yeah, pretty close. Okay. All right, next one, example 5. 3 vertices of parallelogram WXYZ are, W is at -1, -1, 2, 3. X is at -3, 3, 2. Z is at 1, 2, 3, 4, down 1, 2, 3, 4. Okay, so we want to find the coordinates of Y. So this one goes W, -1, -1, 2, 3. So this is W. X, -3, 2. This is Z, which is 4, -4. So we need to find Y, and it goes W, X, Y, Z. So W, X, that means there's some Y over here, and Z. Okay, so we know that we got W to X, okay, and W to Z and W to X. We need to figure out where Y is at. Well, since this is a parallelogram, we know opposite sides are parallel. So this side over here, Z to Y, has to be parallel to W to X. And if they're parallel, they have the same slope. So I'm going to find the slope from W to X. From W, we go back 1, 2, up 1, 2, 3, 4, 5. So the slope from W to X is back 2, up 5. Oh, we need to go rise over run first, don't we? Flip it around. Rise up 1, 2, 3, 4, 5, back 2, up 5, back 2. Or here 1, 2, 3, 4, 5 over 2, down 5 over 2. Well, regardless, it's -5/2. So rise of 5, back 2. So for Z to get to Y, so the slope of YZ has to be the same thing. The YZ slope has to be the same as the slope from WX. So I can use that same slope, up 5, 1, 2, 3, 4, 5, back 2. So there's where Y should be. But now let's double check, make sure, let's do the slope of W to Z. W to Z, down 1 over 1, 2, 3, 4, 5, down 1 over 5. Now let's do the slope of X to Y. Down 1 over 1, 2, 3, 4, 5. Yep, so Y here is at the coordinate 2, 1. So Y is the ordered pair 2, 1. And we got all of that just by using that idea of slope. Oops, sorry. Okay, so if you had any questions, please jot them down, bring them to class, see me. Not, you can go ahead and get started on your 7.2 practice.